Good afternoon, everyone. Our team is assessing climate and socioeconomic impact and regional water security that comprises of Hussein, Stephanie, Carrie, and our professor, Chancellor Smarty. And so starting off, we see that while we see that a lot of water is around us, only 0.009% of water is actually accessible freshwater. And within that percentage, it is actually shared with aquatic life as well. And with 40 US states and 2/3 of the world expected to face water shortage in the decade, it is all the more important for us to understand our water systems. And so as we are facing unprecedented population growth and climate change, it is crucial for us to consider the relationship between our water supply and demand. The fundamental mitigation strategy to reduce water demand would be from water efficient equipments, appliances, and processes, conserving water in our daily living and operations, and also changing our dependency on water within our economy. The other strategy would be to increase our water supply through dams, reservoirs, and water reclamation. And so for that, we also studied the importance of resilience to see how well equipped our society is in withstanding drought conditions. And one of the most notable drought in the last couple of decades is 1960s drought. That is where in the Northeast and the Midwest of the US, the regions suffered from diminished water quality, threatened aquatic ecosystems, as well as a rise in contention between the communities and sector on who should be getting water priority. And the strategies during that time to counter the drought was quite last minute and entail disabling non-essential outdoor water use, daily life water conservation, decrease and shutdown of commercial and industrial operations, limiting water releases and transfer, and drilling for alternate water resources. And so the recognition of the significance of drought preparation have grown since then, but the approach have been relatively reactive rather than proactive. And that is due to a series of things such as the randomness of drought, the limited planning resources, limited quantitative data on impact, and also limited authority from local governments. And so it is important for us to identify the ways in which our sectors can develop to increase our society's resilience to water scarcity. And so for our project, we are framing our project scope to study the Northeast and Midwest regions between the 1960 and 2015. And our goal is to assess the resilience of our water systems and determining the contributing factors of its strengths and weaknesses. And to do that, we will analyze historical trends in the domestic, industrial, and thermoelectric sectors, analyze how population growth and economic shift, as well as electricity generation affect these trends, how technological advancement and policy play a role in shaping the direction we are going with water, as well as finally designing experiments to better understand the impact of these factors.
In order to answer our questions, we first need to calculate the water demand or withdrawals for our sectors, decide on our metric for calculating productivity, and calculate the water supply for our regions. All water demand data came from USGS estimated use of water reports from 1960 to 2015. For our domestic sector, it's the domestic self-supplied withdrawals plus deliveries. For industrial, it is the industrial plus mining self-supplied withdrawals. And for thermoelectric, it is self-supplied fresh withdrawals plus saline for the Northeast region. Population data, our domestic productivity metric, came from USGS, while GDP benchmarked to 2019, our industrial productivity metric, came from US Census, and electricity generation data came from EIA and Federal Power Commission. Next. As to our water supply, our renewable water supply of fresh water is calculated with simulated runoff and river discharge using WBM. The values were then fed into our model to calculate the water productivity of our sectors, or how many people, dollars, there we go. So this was used to calculate the productivity of our sectors. So how many people, dollars, units of electricity, or our socioeconomic factor is being supported by X units of water. So we want to have higher productivity. We want to be able to support more things on less water. Then we compared our water supply to demand in order to assess our region's water security under historic conditions, as well as, as well as performing experiments to test the security with different productivity and supply situations. So in case of the productivity, current versus like 1960 water use, and current versus 1960 or drought conditions. So here we have our domestic sector. We see our socioeconomic driver population on the left increasing between 1960 and 2015. The water demand use, the middle graph, is increasing from 1960 to about 1975 for both regions before decreasing into 2015. Our productivity, the amount of driver, in this case, people supported by X amount of water, here it's 1,000 gallons, gets worse between 1960 and 1975 and only improves above 1960 levels around 2005. So some of the factors we found through our literature review that affect domestic water productivity are water efficient appliances. So in the 1980s, low flow appliances first came on the market, and in 1992, the Energy Policy Act set national water efficiency standards for fixtures and appliances. And more recently, the EPA's Water Sense program started in 2006, labels and promotes products that reach an even higher standard, so about 30% higher than the 1992 standard. A study in 2017 looking at public water supply withdrawals for 1985 to 2010 found that urban counties had greater efficiency improvement during that period due to higher population density with decreased outdoor water use, as well as having more recent improved water systems and newer and more efficient housing. However, the EPA also notes that the majority of US underground infrastructure is about 50 years old. And in 2013, the nation's aging public water supply system had an average water loss of about 16% due to leakage and misuse. Also, similar to the water efficiency appliances, high building performance standard programs like the Leadership in Energy and Environmental Design LEEDS program set standards and rating systems for the design and operation of buildings. So as to our thermoelectric sector, here we see our thermoelectric sector. We can see the electricity generation increasing for both Northeast and Midwest regions, and water demand increasing from 1960 up to 1980 before decreasing to 2015. One thing to note is that in the Northeast, water and water efficiency includes saline water, and it composes about half of the water withdrawals for that region. That means that the Northeast is at a geographic advantage because it can meet half of its water needs without using fresh water. Both regions' productivity increased from 1960 to 2015, and some factors that affect this are environmental regulation. So the Clean Air Act of 1970, which restricts the emission and pollution of particulate matter. This helped to close some old coal power plants, which were less efficient in water use. And also helps to shift from coal more towards natural gas or other forms of fuel. The Clean Water Act of 1972, which limits and regulates through permits the temperature and type of discharge substances into surface water. This helps further push towards more water efficient technologies, such as from once through, which is water taken from a system used for cooling, and then discharged to recirculating cooling, which is water taken out of the system, used multiple times, and then returned. Likewise, the cooling water intake rule of 2002, 2004, and 2014 helped regulate the amount of water thermoelectric plants can intake, which further made recirculating and less water intensive cooling systems more favorable. So this graph just shows or further illustrates the shift away from coal to other energy sources. We can see the fraction of coal in blue of fuel consumed by the electric sector decreased between 1960, the top two graphs, and 2015. The Northeast sees an increase in natural gas, which is more efficient, while the Midwest sees a increase in nuclear, which can be more efficient depending on the cooling type associated with the fuel. This graph also demonstrates the shift in cooling technology for our regions. So this graph shows the once through and recirculating cooling systems that were in operation in 2015, broken up by year of in-service, so when they were installed or went online. We can see that the majority of once through cooling systems were installed prior to 1980, while the majority of recirculating systems were installed after 1980.
And so moving on to the industrial sector, what we see is that industrial GDP have been constantly increasing within the scope of our project, while the industrial water use have been decreasing as seen in the second graph. And so what we see that lead up to in our third graph of productivity is that we see a very positive productivity trend for the industrial sector, particularly in the blue line with the Northeast. And that is in part due to increasing energy efficiency in the industrial sector. So in the 1970s, there was a hike in energy prices. And so that became a motivation to advance our equipment to more higher levels of energy and water efficiency to lower the need for fuels. And so in addition to that, we also have environmental regulations taking place, such as the Clean Water Act of 1972, which push manufacturers to adjust their production processes to limit pollution. And so from that, what happened is that there's a decrease in discharge of contaminants into the water, but also an increase in water reuse and conservation in industrial processes to avoid penalty. And perhaps the bigger impact in all these reasons is the economic restructuring that is taking place that shift our economy to manufacturing focus to a service-based economy at the present. And that is in part from the globalization and offshoring that happened. So in the 1960s to the 1980s, the US have a trade restructuring period, which landed a lot of big trade agreements as well as low toll rates that economically favored imported industrial goods over domestically produced manufactured goods. And with the addition of cheap labor out of the US and less stringent environmental laws abroad, that led a lot of manufacturers to move their production centers out of the US. And so that combos into the rise of the service economy, where the decrease of labor demand due to offshoring of production and the rise of automation plays hand to hand with the increased demand of skilled labor and higher education. With the rise of the digital revolution taking prominence in the late 1900s, that also opened up to more job prospects for the service economy to take over. And that is seen more strongly in the Northeast, as seen in the left graph, where the blue for service is overtaking the gray of industrial.
We have a couple of results from experiments and different analyses we've done. So this is the first major result we have. So we took the combined water use from the three sectors, domestic, industrial, thermoelectric, and that represents our regional water demand. And then that was used to calculate demand to supply ratio. So we divide total regional demand by the total renewable or fresh water supply. And in Northeast, we're excluding salt water, so it's only fresh water in the Northeast. So this graph is showing the percent of water supply used by both regions across the time series. So a higher percentage means that we're using more of our available water supply, which means we're interacting and withdrawing more, we're consuming more, we're potentially polluting that water more. So downward trend indicates improvement, which we see in both of the regions. And the Northeast actually reaches a peak of almost 20% of its water supply used, so that's pretty high. So the Northeast and Midwest, the Northeast has an 8% reduction in its water supply used across a 55-year time span, which is a relative 53% improvement. Midwest is about half of that, 26 relative improvement. But the Midwest also benefits from a greater water supply, greater access to rivers and streams. So it starts off in a more comfortable lower range, but eventually the Northeast catches up. So our first experiment tries to simulate what if productivity didn't improve since 1960. So we simulate population, GDP, and electricity generation continuing to grow in those 55 years, but productivity is restricted to 1960. So we take out all the improvements in technology, infrastructure, policy, economy that Stephanie and Carrie mentioned. So immediately, both regions now have an upward trend, which means they're getting worse over time. They're using more of their water supply over time. So the Northeast has a relative worsening of 51%, and the Midwest is far worse at 170% increase. And that's for when all three sectors are restricted to 1960. So on the right, the bar graphs, we have a sector breakdown. So in black, we have, and this is for 2015 only, the end of the time series. So black is the actual productivity baseline, all improvements included. And the green is if all three sectors didn't improve. So then one by one, we can see which sectors made the biggest difference. So domestic in blue doesn't make that much of a difference because it doesn't improve that much over the time series. Industrial starts to make a significant difference in heightening the water supply use, but thermoelectric is clearly the dominant sector here. So all of the cooling technology changes and fuel type changes that Stephanie discussed are really driving the productivity changes in the two regions. And our final result is a multi-factor experiment where we look at climate and productivity in 4 different scenarios. So first, we're comparing the contemporary climate of the 2010s, and we're looking at a 5-year period, just 2010 to 2015. So contemporary climate in black is actual climate of that time. But then we also bring the 1960s drought climate to the present. Then we have modern productivity, which is includes all the improvements in technology, infrastructure, and so ever. And we have vintage productivity, which is the 1960 productivity where no improvements are made. So if we start on the graph on the left, for both the contemporary and the 1960s drought climate, we're looking at percent of monthly water demands met. So this is supply divided by demand. So 100% means that all the monthly water demands are being fulfilled and satisfied. But anything below 100% means there's a water shortage. There's demands that aren't being met that have to come from elsewhere. So obviously the drought climate has a lot more dips than the black contemporary. The Northeast goes down to about 20% of monthly water demands met, which is very low. But then if we shift to the graph on the right, now we have the benefits of modern productivity, modern infrastructure, technology, policy. So immediately all those peaks are shaved off or completely erased. So for the contemporary climate, the dips are completely gone and we have 100% of demands being fulfilled and met. For the drought, those 20% peaks are now reduced to about 60%. And this is basically a demonstration of how those productivity changes are a mitigation of water shortages. And then for the, that was the Northeast, by the way. I don't know if I mentioned that. This is the Midwest, which is actually starts off far worse. So during the drought in a vintage technology scenario, it actually reaches down to about 7% of monthly water demands met, which is severely low. And then when we switch over to modern infrastructure and technology and policies, most of those peaks are completely erased, but the Midwest is still reaching down below 20% of monthly water demands met. So the Northeast did improve in its individual sectors, especially the thermoelectric sector, a lot more, and also has the benefits of salt water. So just to wrap everything up, we wanted to, in this capstone, evaluate regional water security, but also try to identify strategies to better our water security. So in reducing water demand, we demonstrated that the evolving socio-technological economic changes in the domestic, industrial, and thermoelectric sectors did improve regional water productivity by a lot. So the Northeast improved by 53%, Midwest improved by 26% in the demand to supply ratios. And then we also demonstrated an experiment that if the 1960s drought happened today, the benefits of our modern productivity would reduce water shortages by 2,200% in the Northeast and 685% in the Midwest. So if you put this number in a volumetric number, this prevents a combined 39 kilometer cube per year in water shortages, which would supply New York City with its entire water needs for 2.5 years. The other strategy is to increase available water supply. So we demonstrated in our experiments that even with modern productivity improvements, if the 1960s drought were to reoccur right now, the water shortages would still be severe. So the Northeast would experience a total water shortage of 4 kilometer cubed in its 5-year span in the 2010s, which makes up about 9% of its total reservoir capacity. And the Midwest would experience 17 kilometer cube, which makes up about 4% of its total reservoir capacity. So this really demonstrates that it's not just all these productivity and technology and policy changes that are necessary, but also increasing our available water supply through reservoirs and water reclamation technologies. So looking forward to the future, as society grows, as population and economies and the electricity sector grows, we need to continue this trend that we're on in improving technology, infrastructure, and policy, but we also need to have available reservoir capacities for emergency water storage to both meet those increasing demands of the growing society, but also the growing prevalence of droughts from climate change. And that's it. I think we made the time, right? So I want to thank everybody for joining. I want to thank our mentor, Charles Lewis Marty. And thank you, Catherine. And we'll take any questions.